Oh, hello everyone. Welcome back to Topological 4G Theory with Geometric Algebra, short season 1, episode 4. So I'm retitling these videos shorts Geometric Algebra 4T4G because I anticipate it'll be a while before I get onto Topological 4G Theory properly. Updated the cartoon for today. On the left you've got the Geometric Algebra rotor, which I may be simplifying things a little bit, but I guess you only need the number e, the exponential, an angle for your Lorentz rotation, and a bivector. Whereas the matrix has all these superfluous entries and is very clunky. So that's what we'll do today. Let's have a look at this. So we want to do some Lorentz rotations, right? And these are just called the rotations. So I'll just summarize this for those students who are unfamiliar. Lorentz boost in geometric algebra, or what we're calling the space-time algebra, that'll be for me plus minus, is just a rotation with a bivector parameter. One of the space base vectors and a time-like 4 vector. That's the bivector for the rotations. Some people write this EK, E4 if they're in a particular frame. All right. And what are the rotations? What are the rotors? They're just an exponential of a bivector. Usually you put a negative sign there, I think. Yeah, because anyone who's new to this series will know that I'm just doing these in my lunchtime, so I'm just sort of doing it a bit ad lib from memory. Then you got a rapidity, which is like the it's the arctan. Yeah, in arc hyperbolic tangent of the beta for the Lorentz rotation. So you just have the alpha over 2 here, parameterizing a rotation. And so a Lorentz boost of some coordinates, call them the prime coordinates, will be equal to the rotor sandwich product of the old coordinates, tilde. Okay, so R reverse is just the same bivector rotation but opposite orientation, which in terms of the exponential just means you put a minus sign on the exponential. And that's all there is to Lorentz rotations. Pretty cool, eh? But what about in the old school? I know it's not old school yet because you still teach the stuff, but in the old school matrix algebra, you've got a Lorentz matrix times your vector gives you the boosts. And what is the Lorentz matrix? Well, it's a bit of a pain to code up, but I guess I could do it. If I do, I might get this wrong. If I do coordinates 1, 2, 3, 4, the fourth being time, I think it's a gamma here, and then a let's do a z. Z1's a bit easy to do, I think. Oh heck, see, I've already forgotten, so I'm going to have to cheat and look it up a bit. Oh, hang on. Yeah, no, I had this gamma. I think it's gamma's down the diagonal, and negative gamma times beta. Yeah. A negative gamma beta and negative gamma beta and a gamma on the diagonal here, and oh geez, so this is the pain, right? Yeah, so you only get a diagonal entry on the coordinate that you're boosting. So sorry. So if it's a Z boost, you get a gamma there, and then a 1 along the other diagonals, like an identity. And then of course the general matrix would be something where these zeros, where you get gammas on the diagonals times a beta factor, I guess. And see now you can see the problem. If I do a boost in the Z direction, it's gamma minus 1 beta Z, but that's equal to 1, so it should be just gamma. Yeah. Anyway, the whole point of today's video was to not waste your time on all this and to just code it up. And so let's just see if this all works, right? So to do that, I'll go to my notebook, where I've just put in some Python code for geometric algebra. All this stuff. Oh yeah, so I need the geometric algebra. I don't need the multivectors, but I was using this to type check a few things. I can make this a bit bigger, I think. And yeah, so Python packages. Let's just quickly mention that for students who are not familiar with Python. It's pretty easy to get started. So once you install Python from wherever you get it from, you can use the Python package index. And on a GNU Linux operating system, it's pretty easy. The two packages that I was using was galgebra and simpy, but I'm not sure if it's called simpy. I've already installed galgebra, so this should just tell me that it's already installed. It requires simpy. Galgebra is nice. It uses symbolic Python. And yeah, so it was already installed. There's a search. Pip doesn't support search anymore. That just tells you to go to the website. But there is a utility called pip_search which you can use. And so I could search for simpy if I didn't have it installed, and I'd look for the package name. You know, so if it was as pandas. Oh, pandas has symbolic algebra. That's cool. But there is a proper simpy package. It's just called simpy, so I'll put that in there. And it would install most of the dependencies that I need. There's also this one called Lorentz, I think. I think that's the name of it. I'm not sure. Yeah, so you can install that too, which I went ahead and did, but I found it not very useful because it's dealing with momentum, and all I wanted to do was check kinematics. But if you wanted to download it or import it into your notebook, you'd use that. For my matrix version of the Lorentz boost, I'm just using NumPy. This stuff you don't have to put in your code. I was using that previously. You don't need these. I did use T4GU as symbolic coordinates because I didn't want to do a specific coordinate transformation. I just wanted to do the transform symbolically and then check it. But this is the key line to define the geometric space-time algebra, plus, 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 minus. And I do use these symbols. But then I avoid the symbols by aliasing the geometric algebra to basis vectors E1, E2, E3, E4, which I usually think of these as gamma 1, gamma 2, gamma 3, gamma 4. And I define my Pauli bivectors, which are isomorphic to the matrix Pauli matrices, but I'm not using those today. So here we get to the first bit of code for the Lorentz boosts. I was just checking these just on the command line, so I just copied and pasted what I did on the command line. So let's just quickly go over this. The beta parameter is the ratio of your boost velocity to the speed of light. I'm taking the speed of light, c equals 1 here. The rapidity of the boost is the inverse hyperbolic tan of the beta, and then we get the gamma factor. Everyone who's done special relativity should know this. I'm assuming you've all done a little bit of special relativity at high school or first year university. That is what these shorts are aimed at, advanced high school or freshman or sophomore university students. Everyone else should just go away and learn some geometric algebra somewhere else. I'm only going to do the basics here. And then this is a geometric product. If these E3 and E4 are multi-vector types, then asterisk is the geometric product. If I wanted to do the wedge product, I could use a caret. But because they're orthogonal and anti-commuting, it's the same. The geometric product will be the wedge product for those. If I use the asterisk operator with a scalar, like alpha, it's just a real number or a floating point number, then that just acts like normal scalar multiplication, as does the division here. So this is my bivector, B for the Lorentz boost, just as I did on the, that's what I did somewhere here. This is, yeah, so it's this is the bivector here. So what did I do? Oh, I did an E3 and an E4, so it's a Z direction boost, E3, and the time direction E4. And then I compose the rotor by exponentiating the bivector. In GeoGebra, you do that with a each multivector has its own set of special functions you can call on it. I don't think it would work if we used like a Python math thing like that, because it wouldn't know what to do with it. So the multivectors have their own functions that are defined on them as methods. Okay, if you don't understand computer code or Python, that's something you'll have to learn. I'm just going to skip any Python language stuff here and just try and concentrate on the algebra. Okay, and then I just wanted to check each of the different coordinates. So it's like I'm boosting the unit vector in the x direction here, basically. But E1 and E2, E3, E4, they're not vectors. They're basis multivectors. They just happen to be grade 1, which is called a one vector. So they're a little bit like a vector. But if I print them out, all I'm going to get back is a symbol E1, or EX, I guess, EX, EY, ZET. I'll get EX, EY, ZET because that's the way I defined the algebra here, EX, EY, ZET. I better run these, right? So run that, and then I print out the results of this transformation. And yeah, so I think that's right. Why am I? Oh yeah, so I just printed it twice out. I don't know why I did. Oh yeah, so I was checking to see if it agreed with the these last two lines. Just checking it agrees with the sort of hand calculation of the Lorentz transformation, which is your transformation using your gamma and beta directly in just a single expression. So I was just checking that. I should say though, once you understand the space-time algebra, you'll think of the Lorentz rotation as a rotation like this: r times the vector times r reverse, as far more simple and natural. So you'd really want to be checking everything against the space-time algebra, not the other way around. And that's kind of what I ended up doing this sheet. So for example, I wrote a quick function to do the same thing for the using the pi Lorentz library, but I found that not to be useful. It was okay for doing a boost, checking a boost in one particular direction, which I did here, but I'm not going to show you that. What I wanted to do instead is just write a general function using the geometric algebra for any boost. So I put in the arguments will be the direction of the boost, which I just call v, and the beta factor from which you can get both alpha and gamma. And then I just for comparison later, I put in an optional type argument, so that the output can be either a dictionary or a matrix, numpy matrix. You just choose one or the other. Either put a D here or an M here. It could just be D if you want, or M or mat for diction. Okay, now let's just go through this again. Locally, I'm redefining these x, y, z, and t's just for the local function. They'll disappear after the function exits. And so I'm redoing a little bit of what I did here, but firstly I just got to normalize this vector. And so whatever the vector's components are, x, y, and z components, I multiply these by the basis vectors in the geometric algebra, E1, E2, E3, which are the same as EX, EY, Z. And then I use numpy to take the norm of this. Actually, no. Yeah, no, this is this VV is now actually a multivector from galgebra. And galgebra has this norm function built in. So I can just use the built-in function to take the norm or magnitude of this one vector. Note that it's a one vector. People might call it a three vector because it's got three components. But in geometric algebra, it's called a one vector because the grade is one. It's only made up of vectors, no scalars or bivectors or trivectors. And so once I've got a unit vector in the direction of the boost, I can wedge that now because I don't know that it's a pure base vector, right? It's a combination of these three base vectors up here. So I can't take the geometric product anymore. That would be an error. I need to make a wedge product to get a proper bivector. And then but this is really interesting, this line here actually, because it does everything in one without any coordinates. I don't have to separate this rotor that I'm about to define. I don't have to separate it into an X rotation, a an X time plane rotation, a Y time plane rotation, and a Z time plane rotation. I can do them all in one. So this is wedging the time-like basis vector E4 with each of these three components or blades, blades of the boost direction. A blade in geometric algebra is just a pure grade object. So if all that jargon confuses you, just ignore it for now. You can learn it later. So then I'm just going to do the boost. So to do the boost, you just rotate the multivector that you want to boost. So my multivector is this symbolic expression here. I use the SIMPy symbols x, y, z, t, and obviously x is going to be in as the coordinate, symbolic coordinate. It's not a real number, right? It's just a numpy symbol here, and so that'll be the total, the object that I want to rotate is this thing here in brackets, and the rotation is just the same as before. You multiply by geometric product on the left by the rotor, and on the right geometric product with the reverse of the rotor. The rest of this is just superfluous, but it's just I did it for printing things out. And I guess this is the little lesson from today, is how will I take this boosted multivector, which is when you rotate a vector, it turns a vector into another vector. So this is just going to be a grade 1 vector, but it's got components in each of the base directions. And so how do I project out the components to compare with, say, a matrix version? And on episode 3 of these shorts, I think I showed you, well, I just had a guess. If we want to project a vector, say A, onto a bivector plane, say B, then it'll be a projection onto the plane. I guess you could call it A parallel. Will be the simple dot product. That's what I said it was. It was like projecting, but I forgot that you actually have to divide by the bivector B to sort of, it's a normalization, right? But it's not the norm of the B that you divide by. It turns out it's the whole thing B. And because B is taken to be not zero, not the zero bivector, it'll have an inverse. So you could also do it like this, B inverse. And the galgebra package has a operator for this, a method that you can use for any multivector, and it will do the projection for you. But it doesn't do the B negative 1. So if you don't do the B negative 1, if you don't do that, what you'll get, so here's the example line here. If I don't multiply by the inverse of E1, which is the vector that I'm projecting onto the one vector now, not the bivector. If I don't do this inverse, then all it means is that this expression here that I've just highlighted, project in the blade, it'll still have the E1 direction attached to it, which will print out as EX or something like that. So let me quickly do that for you. Here's a little demonstration of that. So I just made up a vector with a symbolic symbol A1 and A2 and floating point coefficients as well, 1.1 and 1.2. So if I project, yeah, so let's just copy that. So if I take P and project it in the blade E1, what do you think I'll get? Let's just run that. I get the projection, which is A1, 1.1 times A1. That's my coefficient, scalar coefficient. But I also get this SIMPy or galgebra symbol for the basis vector as well. So to get rid of that, that's what you do. You just multiply by E1 inverse. And that will just get rid of the EX on the end here. So that's just a helper function that we can use. This box here, line 4, is just some help. Just some mucking around. Okay, so that's what I've got there. I guess I'll try and post this on the GitHub for anyone who wants to play around with this. And then I did a helper function, changing the boost into a, here I use it here, I changed the boost into a matrix. So the default output is this dictionary, which includes entry for the gamma factor, just in case you want it for, you know, doing relativity, mass, energy stuff. So that's the default output if the return type is a dictionary or D. But if the return type is anything else like a matrix or M or something, I want to convert that to a matrix. So I just had to write this particular function here. It's not difficult to do. You just do numpy matrix and you pick out the components using the dictionary here that I defined, which already projects out the components for you. But I just have to get rid of the square roots, any surds, because SIMPy, if it detects like a square root of 17, it'll actually display square root of 17 instead of the floating point numbers. So eval f is evaluate as a float. It gets rid of the those square roots, and that's just because if we do the matrix version of the Lorentz rotation, it will get rid. It won't have any square roots, and so we want to be able to just directly compare the floating point numbers out of these things. Yeah. So lastly, I just wrote this helper function, which is just to compare two Lorentz rotations. One using the geometric algebra matrix that comes from this function here, and the other is the Lorentz boost matrix from the matrix algebra version of it, and you can put in whatever tolerance you like. It's usually pretty good to 15 decimal places in the float. This could have been an awkward function to write because you've got to do 16 pairs of numbers to check, which would be, here's the first 16 for the geometric algebra matrix, and you just redo all this for the Lorentz matrix and then compare each of these values. But you know, you can use some loops to shorten that code up a bit, so I can get rid of those. Don't need those anymore. So all I do is I go through setting either the x, y, z, or t value to 1 in the substitutions for SIMPy, and this just substitutes the symbol x for the value of x value, and normally it'll be 0 because I start off with them all being 0 here, 0, 0, 0, 0. But depending on the value of n that I'm in the outer loop, one of them, either the x value, y value, z value, t value, will be equal to 1, which will pick out that particular component from the matrix. And the other component of the matrix, the row, is just going to loop from 1 to 4 as normal. And then finally, once you've done that, you can just check that the two entries of the matrix that you're in on the inside loop have a difference that's greater than your tolerance. And if any one of them is greater than your tolerance, then you can immediately return a false value. If it passes all the tests, then it drops down to return true. All right, so I better run these things. I forget what I'm up to. Did I do that one? Just check that I haven't got any errors here. Okay. And now we get down to actually computing the matrix for, here's a boost in the 1, 2, 3 direction. Now that'll get normalized when it goes into the function, and the beta parameter is 0.9, and then it just you get a matrix out of that. If you make up a symbolic matrix using X, Y, Z, T symbols, turns out NumPy can handle that. It knows how to multiply symbolic matrices from SymPy. I don't know how it managed to do that, but there's some operator overloading there, and so you actually do get the matrix out of that. So the X coordinate has gone to negative 0.55 times the T coordinate plus blah blah blah. So that's a general Lorentz transformation, some arbitrary direction. I just chose 1, 2, 3 just as an example. So that should run, and I do want a check in the, this is a Z direction boost in the Z direction, so you'd expect the X and the Y boosted coordinates to be unchanged, which they are. And you can compare with your answer before to check that the gamma beta is the correct. I think it worked out correctly. And yes, I did read the calculation here just quickly by hand. Gamma t minus beta z is the new t coordinate, time coordinate, and the new z coordinate is gamma z minus beta t, and that seems to work out. If you squint your eyes closely, you'll see the negative signs are all correct. And just some code that I commented out, similar thing. Yeah, so then I redid the boost calculation using the one-liner. The one-liner is to use the function LBoost that I wrote, and that computes the matrix and then multiplies the matrix by the XYZT vector, and you get the same result. It's all good. Now I do the geometric algebra boost, which is a lot quicker to run, and because you don't have to do so many matrix multiplications, most of them is it's just a much quicker calculation, even though it's using SymPy. And right, it should be the same, 0.551. Yeah, the last one, 1.6547. Seems to even go to the 15th decimal place. All right, and so that's just defining the matrix using the GBoost matrix, and then the boost dictionary from the this is the call here. Boost dictionary equals GABoost, boost direction of beta. And remember the R type there was just the default D for dictionary. If I did an M for matrix, it would be equivalent to actually doing this call here, boost to matrix. So it's really dictionary to matrix. All right, so, and then lastly, I use that little helper function just as a quick check to see if the geometric algebra boost and the Lorentz matrix boost are close enough to each other, checking coordinate by coordinate, and it is true. So that's all I've got for you today. Just wanted to show you that geometric algebra can be used very efficiently in computations, and what we've done is we've checked the we used the matrix to check this today, but I think it's superior. It's actually better. I don't know. I reckon I can use this to check this. Is what you really want to do. Use the geometric algebra to check that your matrix is correct, because really the matrix is the clunkier way to go. So that's what we did today. Get used to using geometric algebra, and you'll end up using the geometric algebra to check all your clunky matrix code. Okay, like and subscribe. Let me know if you want to do any other topics. Just remember that these are not in particular pedagogical order, although they'll be roughly kind of building up in detail and complexity and getting onto more advanced topics as I go along. But these geometric algebra for topological 4G theory shorts are really just intended to cover little brief topics as I feel like it. No particular order, but roughly pedagogical order, very roughly. And if you need any help learning the basics of geometric algebra, just, there's plenty of resources online. I really don't need to do a video series introducing geometric algebra. You can do that for yourself, or if you like, you can check out my website, which is T4GU, that's topological 4G on theory unchained. It's a gitlab.io website, and back as /T4GU is the home directory. All right, see you next time. That's all for today.